Now we're going to look at how a flat mirror makes the images we see. So all we're concerned with is one side of the object. We don't want to ray trace everywhere. That's what gaming systems do. Okay? We don't want to render a perfect image. We just want to get started. If I give you this graph paper grid, you can ditch the obnoxious protractors, which never work and frankly represent a choking hazard. So, and don't ask about that story. So the first thing you want to do, a free mark. Send a beam of light straight to the mirror. And come on, you kick a ball straight to a wall, it's coming straight back out. This is the easiest mark of all on any ray tracing, okay? Now somewhere out here, you may be watching this and your brain knows, you know the object is here, but your eye, all the associated parts of your brain that do images goes, no, I saw that sucker come from back here somewhere. So the real beam of light ricocheted right off the mirror, but your brain backtracks the ray here. Now, let's see what happens if we send the light in a different direction. I'm going to send in a beam of light higher to here. The higher you go, the better your result. I'm deliberately staying low because I don't have the screen real estate to do this. Now, what made me pick that point of light? Doesn't matter. You can do any beam you want. You have an infinite possibilities. You just have to hit the mirror. But going to here would be foolish because you won't get much of a distance. So your second and third ray, make them as far away from the first one that you can. Now, you're supposed to put a normal on this, but you don't need to because I've done that for you. See? Huh? How nice I am? You don't have to go to that effort. I've saved you that effort there. Look how much time I've saved you. I put the normal in right there for you. Okay? And do I get any thanks for it? No, not at all. So, I didn't say anyway again, I hope. Look at this here, that gap. We need to measure that. We need to measure this angle. But I don't have any protractors. How do I measure that angle? Like my construction worker father, you don't use angles. You use distance. Right there. This purple or blue, whatever color this happens to be, line is exactly 2 squares down from the normal. So it will ricochet 2 squares up. No protractor, no problem. You can match angles by simply matching distances. It was 2 squares below the normal, so it will reflect or ricochet 2 squares up. It will take off like that. Okay? And now your brain's going to do its backtracking game, and your brain's going to say, I saw it from out here. Now here's where I run into trouble. I can't really get that straight line without doing this and overlapping my other one. So there's the crossing. If I try it freehand like this, I have a bit more trouble getting my aim. You won't with your ruler. Now that you got that, let's go do the low beam and not bother with the normal because I've given it to you. Start here and send a beam in low. Hit one of these grid lines. Don't put it there. Hit it exactly where one of these lines is, and now you don't need to use your protractor. So how far away from the line am I? Well, look right here. Don't count from here. You don't have enough room. If you go all the way up here, here's the normal. I'm not highlighting it. We are 1, 2, 3, 4, 5, 6 squares down is where that is. So if I go back to where this normal is, I can go down 1, 2, 3, 4, 5. I went off screen. I don't have the room for it. I know what I'll do. Look, right there. There's another intersection. The orange line is right there on a square. 1, 2, 3, 4 squares down. I'm on the normal. So I would reflect 1, 2, 3, 4. There it is right there. Yes, that's it. That's the bounce out angle. In this way, bounced out that way. And I didn't have to draw the normal because my teacher was so nice. He included a normal for free right there. So that's what the graph paper's for. Now, where did your brain think it came from? Your brain out here thinks it's such a smarty pants. Your personality may know the light is over here, but your eye is totally duped. Your eye is like, I know where it came from, way back there. So once again, the condition of an image is all the light from this point is the arrowhead. For you to see it, you have to gather all that light. In here, your brain thinks it sees, well, it doesn't think it sees, it does see the replica light coming off of here, but it triangulates it back and it swears it sees the arrowhead there. So in here, you draw your arrowhead. So you go in and you go, I'm going to draw an arrowhead, and you scribble away there. There's my arrowhead. And you've done it. You've found the location of the arrowhead, even if you do the scribbling really bad. But what about the tail? Well, then you have to repeat the ray tracing for the tail. And then you have to repeat it for the body along the way. And you're going to take 3 years to draw it. And I'm going to take 3 years to grade it. So let's say you found the tip, and the computers can do the rest. So how do you locate the image of the tail? Well, think about it. If you are 1, 2, 3, 4, 5 steps in front of a mirror, your reflection will be 5 steps behind. So the tail of my arrow, where's round? Where's round? 5 steps back. 1, 2, 3, 4, 5. Tail of my arrow should be right there. Okay? So I can draw my arrow. It's going to be something like that. There it is. I can straighten the head later. That's the image in a plane mirror. A little bit obnoxious to do, but not terribly, but fairly straightforward. Send one in high, then you'll take the high road, I'll take the low road kind of thing, and you got your 3 beams intersecting. Just there is no light on this side of the mirror, which is why we draw it in gray. There we go.